welcome to another lecture of linear programming. We have been looking at minimax theorem, and just to put you in the context again, remember the idea was based on a two-player zero-sum game, right? That means two players were playing, they had strategies. In this case, how many strategies did player A have? M, right? Row player had M strategies and column player had N strategies, and we assume they can even play probabilistically, right? So X is a distribution over all possible strategies of the row player. Y is a distribution over all possible strategies of the column player. M gives the payoff. We can say that there is the money which column player will give the row player. In case, so Mij is the amount of money player B will give player A if A plays I, B plays J, right? And then this is kind of the payoff if Alice row player plays with X, column player plays with Y, right? And then we saw this Max-Min theorem. It basically says that there exists a point. The point is this X comma Y where this min-max will become equal, right? At this point, there is no incentive for the column player to switch the strategies. There is no incentive for the row player to switch strategies too. And this is called the beautiful mind, Nash equilibrium, right? This is called the Nash equilibrium in this case, right? So this shows that Nash equilibrium also always exists in two-player zero-sum games, and it's a direct, in some sense, corollary of what? Strong duality, right? Today, we are going to see another application of this nice theorem, and it will take us places. So you will see how important these ideas are in very, very different applications, right? So I will start with data structures, right? Why do we use data structures? How many people have done a course on data structures? You don't have to raise hands. I know everyone has done it, right? Rhetorical question. So yes, why do we use data structures? Very nice, right? So it's a format so that we can quickly run some algorithm or quickly run some task, right? Efficiently is a very nice important word. We want to efficiently store our data so that some questions, some algorithms can be answered quickly on that structured data, right? And a very simple model, don't worry about complicated data structures, but a very simple way in which I can think of data structures is that I am storing my data in memory cells. So this is one memory cell, and every query I can fetch one of these cells, right? If this is the case, then in some sense the efficiency is decided by three things. One is number of cells used, let's call it S, okay? Second, I can say word size or W. What is it? It's the number of, what should be the word size? Intuitively. In the cell, right? It is the in the cell. And generally data structures are optimized for a particular kind of question or an algorithm, right? So if I have a question in mind, what other thing I want to what other thing I want to optimize? Time, right? Time in this case would be number of memory cells I will fetch, right? So I will just call it queries needed, right? And not generally it is queries needed in the worst case, for the worst possible input, right? And this I will call T. And now, depending on the problem, you might have different kind of data structures such that these things will take different values. But generally the idea would be to say that, okay, if S is very small, then W or T should be high. If these are high, these are small, then S should be high, or some mixture of that should be high, right? That's the kind of thing we want to prove as a complex J theory. You want to say it's not possible to do it, in just with one memory cell with one bit or something, and you will always answer efficiently. You want to say that some task is hard, some task is difficult, if some combination of this thing is always going to be high, right? And this will stay at the intuitive level, but this will make sense. So let's try. Let's take an example, right? And my favorite example, suppose IIT Kanpur has a master list of cheaters, people who habitually cheat, right? So this is the master list with IITK, right? And they want to encode it, keep it in some data structures, and every time one of us instructors find whoever has cheated, we want to find out if those cheaters, one of them is a habitual offender in that master list. The question is clear? And now, since IIT Kanpur students cheat a lot, this has to be done a lot of times, right? Every course consistently is trying to, so that means I need to store this efficiently. I need to store it so that quickly I can recover this. Jokes apart, what am I planning to do mathematically? What operation I am performing mathematically? No, remember this is a master list. I have some list of students who have cheated. I want to find out if there is a person in my list who is also present here. This is set intersection. And you can see that in spite of this made up example, there are various cases where set intersection is an important problem, right? So data structure wise, the problem is a set is stored already, right? So you want to store a set, or let's call it Y because X is generally the input, or it's hard to cross out X. Z, this is store a list, store a set, and then once the input comes, I need to answer whether this is equal to phi or not, right? And you can see that this has many applications, right? So now if you want to store, how would you want to store it? And again, remember, these are the important criteria, right? What could be the possible ways to store it? Suppose the number of students, the universe size is known to you, n number of students. So what could be the possible strategies? How can you store? Okay. Let's not worry about the randomized case. Let's worry about deterministic. So let's start with the simplistic. Right. The simplest one is you have the set S, right? And set Z and X as binary strings, right? In 1 to the n. Clear? Let's say for this simple representation, what is my SWT? What is S? S is n, right? But I can say that okay. If S is n, you are saying W to be 1 and T is n, right? In the worst case, correct? What I can do is I can even say that I am storing this as words of length W, and W could be a parameter. In that case, W is W. Right? Now, suppose I was only interested in T. Is there a better way to store? I don't care about S, let's say. Array of bits of what do bits represent? That is what exactly this was. right? This was exactly what that was. So now suppose I only care about t. I have a lot of space. What would be your choice of representation? Very nice, very nice. What I can do is I can store all possible intersections. Correct? And in that case, t will be 1. Right? And not to belabor the point, but you can also say that, okay, I will store all possible intersections of sets of size less than some size p. Okay, that will decrease s a bit, that will increase t slightly. So there is a trade-off where you can reduce s a bit, but t will increase a bit, right? So because every set z can be represented with at most n by p sets. And I just check the intersection with all those n by p sets. So then this could be, and t would go like n by p. Like that is the number of sets in which I can divide, less than p, right? So all this, so again, this is not the main intention, but what I'm trying to say is that there are various strategies and there is a lot of trade-off between these quantities. But you also see that if I try to decrease one quantity, other quantity will increase. And this is true. You can show such kind of results, but think about how hard it is. Because there are so many parameters and every time there are so many strategies, right? You can get an intersection, and if you want hash functions, you want BSTs. What you want to show is whatever thing you do, whatever you have learned in your data structures course, you can't do better than some critical threshold, right? So you see how hard this problem is, right? But if you want to give a lower bound, you want to capture something which is intrinsic to this problem, right? What do I mean by intrinsic to this problem? One way to notice that would be to say that, let's say X is the input with a party ls, okay, and this data structure is with Bob. Y. Okay, sorry, data structure was Z, right? Should remind me, right? So data structure is with Bob, and now I don't know what Bob is doing. I don't care. Whatever Bob does, I want to make sure, I want to count the number of bits they communicate between each other such that at the end of it, I get X intersection Z. This is the idea again, right? It turns out that this is a very, very successful model. This is called communication complexity. How many people have heard of it? Okay. So this is called communication complexity, and this is not just useful in data structures. You can give VS circuit lower bounds, you can give data streaming lower bounds, you can definitely give, like, the good bounds on this kind of a thing actually comes from studying these kind of problems. And this is what we call set disjointness problem, which is a canonical difficult problem for communication complexity. Okay? So what we want to see today is how to give lower bounds in communication complexity using minimax theorems, right? Using linear programming. So a very natural problem in data structures where it seems it's very hard to give lower bounds, we will see actually that those lower bounds come up by first abstracting out what is difficult in this. We are trying to say that however you store the data, some bits need to be transferred. And that means at least one of these things will be high. So this is the first abstraction which took a lot of time to develop and was a major insight. I'm giving it in 5 minutes, but definitely it's a huge deal. Right? So first it turns out that to give lower bounds in this model, you can reduce it to lower bounds in communication complexity. And not just in data structures, but in streaming, but in circuits, in many cases lower bounds reduced to communication complexity. This is the first thing. I have only given an intuition for it, but now we will see how to actually give bounds in communication complexity. That would be more rigorous, more robust. But is this kind of an informal idea clear? How you can give lower bounds in data structures by giving lower bounds in communication complexity. Actually, communication complexity obviously has two parts, giving nice protocols and giving nice lower bounds. But for these kind of applications, lower bounds are more important. But if you are mathematically inclined, the protocols are amazing. You should read about some protocols for communication complexity, how smartly they solve problems. It's a lot of fun. Though, for today, we are interested in lower bounds. Sorry. Sure. I will generalize the problem, okay, and tell you the generalized problem, and then you see that match up. The general problem is I have two parties, Alice and Bob. Alice gets an input X, Bob gets an input Y. Okay, and in the background, I have a function in mind, which gives me a value in, let's say, whatever, set Z, or actually, let's simplify, 0, 1. Okay, so I have a problem in mind. Alice gets the input from X, Bob gets the input from Y, and their task is to calculate f of xy using I don't care what they do here, right? That is, I assume that they are all powerful. They can store Y whatever way they want, they can compute on Y whatever things they want. I don't care about it. The only thing which I want to minimize is how many bits are transferred between these two parties. Right? For example, remember in this case, I can say, oh, they compute all possible intersections with all the sets and keep it around. Right? Even that was fine with me. I never said, oh, how expensive it is to, calculate the intersection. So to capture all these kind of data structures, I am here saying, I assume these are all powerful. The inherent difficulty in this task is that some part of information of X should get transferred to Bob, or some part of information of Y should get transferred to X if they want to calculate fxy. And since they want to calculate fxy, they will have to create some amount of communication. If you give lower bound here, it will give you a lower bound for this kind of task. So now, what is fxy in this case? X intersection set. This is a set of all subsets of n. This is a set of all subsets of n, power set of n. And this is saying whether there is an intersection between these things. You mean to say, oh, in terms of computationally, so yeah, let's say they have Turing machine of infinite power, like Turing machine of infinite power. That's good enough? Though actually, yeah. Okay. Now, yeah. So now, this is the model. How do we give a lower bound on that, right? And even in this case, there are deterministic strategies and there are randomized strategies, and we will see how to even give lower bound in the randomized case. Okay, but what does it mean for the protocol to be correct? Right? There are many inputs. In the case when I have a fixed protocol in mind, what do I mean by the cost of the protocol? Because it might happen then on some x and y, my protocol sends only 1 bit of communication. For some x and y, it sends 100 bits of communication. So what should be my measure of how many bits am I exchanging? Worst case, right? Like we talked about here today, right? It has to be worst case. So generally for deterministic protocols, I say whatever this worst case is the most important measure which we study, max over xy bits communicated with x comma y. Yes. Input.